So again, same as last week, I am recording. If you don't want your voice recorded, put your hand up. I'll pause it, then you can ask your questions. No hassle. Okay. Just do it like this. So the material for last week, I'm sure you've all had a look at. The material for this week. Whilst I'm on that, before I go on that, I know there's at least 2 people here that weren't here last week. Just give me 2 minutes and I'll very quickly go over some of content. So there are some books here for further reading. I would say that this module, everything that you need to pass the module is within module content. However, if you want to do a bit further reading, you want to know a little bit more or where a lot of the stuff comes from, these are just some of the books that you can have a look at. I would say just be mindful of your time. You have got 3 modules. You've got a maths module this term. Yeah, so just be mindful of your time. However though, I will be giving you additional books I consider actually very worthwhile, hence why I'm giving them to you. Only a couple actually here. Well, so I brought this book out last week, but there it's here for you. I'd recommend you download it, keep it. It takes from total beginner mathematics all the way through what you need for a PhD in engineering, but it's all through application. So it's examples of. So your mathematics that you're doing just now, what are you covering in there? Matrices, yeah. So I think you do that in 3rd year, you do it in 2nd year. Well, you probably do it a bit more in 3rd year as well. Like matrices are so vital when it comes to FEM and finite element analysis, finite element method. It's based on matrices, the whole thing. You will not understand, if you can't do mathematics using matrices, you'll not be able to do FEM as a module at all. It just won't happen. This book's fantastic. It gives you all sorts of examples for everything to anything. Right, I'll stop boring you about that. This document here, BSEN 408. This is the document that this module is based on. So it's all the tests that you'll be doing in the lab downstairs anyway, and most of the tests in the lab that we'll be doing in my office at Seven Hills, near Sight Hill, will be based on this document here. I don't recommend you download it. I demand that you download it and you read it, and you'll have to read through, not the whole thing, because it's a fair sized document. You will need to read 40 pages. You will need to read through the about, 15 pages that are relevant for this module before the certain lab sessions. I'll explain more about that as we go on. But what I would recommend you do, that you do download this document today. And do have a look through it, at least so you can understand. You already know what tests you're going to be doing. It's compression, perpendicular to grain, parallel to grain, if that's the piece of wood. I should have brought something with me. Then you've got a 4-point bending test. These are the 3 main tests that you'll be doing. So you already know what they're going to be. So download the document, have a look through it, and you have to look. Well, we'll cover that in more detail later on. We'll give you more books as this module progresses, but these are the 2 main ones I would stick to at the moment. Right. I'll give you this here. That's an extract from that book. That was just me doing very, very simple. You need to be able to manipulate equations in today's class and all the classes going forward. This is a very quick, just to jog your memory how to manipulate an equation. And just a literate extract from that book. So that is, I've given you that. And a quick summary, it's going to be a closed book exam I have for this module. It will be closed. No one's came forward to me. I don't think anyone's got a learning profile. So, all good. I'll decide what I do give you and what I don't give you. I'll give you an example. There's an example here actually. There's my notes from last week. If I were you, I'd be making notes, and that's what I would have written down, the equivalent of last week's module. This week's class, sorry, is the equivalent of that. I'll be writing stuff down, but you won't. I'll decide if I give you any of this at all. I will not give you as much as that. I think we'll make that decision in the next 2 weeks and you'll know exactly what you'll get in the exam, if it's totally closed book or if I'm going to give you a document to go along with the exam. You will have to remember some of the equations. If that is a problem for you, I know it is for me. I've got short-term memory loss because of my dyslexia. If that's a problem you've got as well, come and talk to me. We'll have a chat and I'll then decide what the class gets. If we do it for one, we do it for all. Makes sense. What I would say though is a lot of these equations are quite repetitive. We'll look at different parts of what we do through this module, and it's the basic same structure. So if you can remember about 5 equations, you could probably muddle your way through all of them. And it sounds a bit weird at the moment, but you'll get the grasps of it. Right, let's go back to the middle page. So for this week then, this is week 3, believe it or not. There's the lecture slides there. I will be giving you maybe a URL for today's recording. I'll remove this old one. We'll have an additional tutorial each week because we've got a reading week this term. This module used to be in Try 1, it's now in Try 2. Because we now have a reading week as part of our terms now, I've lost a week. So there was an exercise that was a formative assessment. Just a recap for the two, I'm saying. So there was an exercise that was a formative assessment that took a whole week to do. We're not going to do that now. So what we're going to do is each week I'm going to set you homework and you're going to upload it to me, okay? Now it's totally voluntary. You don't have to do it if you don't want to, but if you do it, that's your time and effort. I'll put my time and effort in and I will mark it and give it back to you digitally, so I'll make comments. And how you'll do that is you'll upload your question into there. So it's totally voluntary. If you want to do it before next Monday. Preferably do it for Friday to give me the weekend to look at it. Otherwise Monday morning I'll be trying to do it 5 seconds before the class starts. If it does become problematic for me, I might just literally jump up the answers in the class and pull out, do screenshots without any names of course. What people have done, where they went wrong and why they went wrong, type of thing. We'll have a look at how we give feedback, but that's formative feedback. So you're asked about formative feedback, at least you've got the opportunity for it. Right. Cool. One more thing, just a bit of housekeeping. Should have talked about this before. Yes. Next week we shall have session. It's totally voluntary. It's E32. Highly recommend it. And it's using Microsoft Excel. I know everyone's used Microsoft Excel, but I'll be getting you to do things you've probably never done before in Excel. The reason for that, the data sheets that you'll be getting for this module will be absolutely massive. It'll be about 8,000, 9,000 lines of data you'll be getting from these machines in the lab, and you'll have to process that data, and knowing how to use Excel at its best is what you need. So I'll be doing that in these tutorial sessions. Try and make all of them. If you missed the first one, not a massive deal. I do have a word for word what to do step by step. But I know because there's no class in between. These ones here, at least there's a lab session in between. That last one, we'll see how we get on if people are struggling with their hand-ins. We keep that one or not, that last one. Okay. And there will be another lab, again at Seven Hills, which I've not got a date for yet, but I'll let you know. Again, that'll be voluntary, but it will be actually really quite interesting. Rather than testing small samples that are about that length, which you'll be doing, we'll be testing a sample that'll be like maybe the length of the room, perhaps. Using the exact same everything, just a much bigger machine. Depends what Voitech's testing on the day. Right. What do I want now?
Sorry.
I'm doing, how you doing? Checking code. There's a checking code there. Right. Okay. This will work. And now it. It's worth a thought. Right. Okay then, so this is lecture 2. There's some tutorials in this lecture. What we're looking at? We're looking at the axial load displacement and normal stress strain. I know we've covered a bit of that before, but we're looking at it in much more detail today. Remember what we're trying to do? We're trying to understand what happens in the material. Where these simple equations come from. You know, the equations for bending moment for a beam. We want to know where they come from. That's what we're going to try and do by the end of this module. So today we'll be looking at the axial load displacement in a little bit more detail. We'll be looking at the Parsons effect, and stress, and we'll have some exercises. So it's fairly straightforward. So a bit of recap from last week. I'll stand to the side. You remember this F force, so the force pulling down. That's equivalent to K divided by L delta. We have to eventually work out what KL or what K actually was. If you remember that. The delta was just the elongation. And we write that as Li, which is the Li is the new length. Take away the original length. And the actual axial strain, stress strain. So we've got stress there and strain there. Try and remember what the symbols mean. So stress is F over A and strain is delta over L. Again, it's just a recap from last week. One of the good things to have a think about though is try and make sure you can remember also what units they're in. That's very, very important for manipulating your equations to get out what you need. If you're trying to get a certain thing, help you if you can remember stress and strain, what units they're in. I think the easy way for me, how I would do it in the past, I'll still do it actually. Stress is my force. So if I've got a load of a kilonewton, I've got it on a big area like my hand, say. Or I've got the same load, but on a point of a pen. Stiletto heel, isn't it? That stiletto heel effect is going to be much more damaging, far more damaging than if it's on a bigger area. Literally, I heard this years ago, somebody said that a woman's stiletto heel can equal the stress of an elephant's foot. Elephant's much, much heavier, obviously, but it's got quite a big pad of foot. But a stiletto heel, a person's weight on the heel, it's just a point load. So try and think of that as force over area, and the axial strain is just the elongation divided by the original length. Right. And then we have this Young's modulus of elasticity, or MOE, or just elastic modulus. We call it different things, depends on what book we're reading, but we write it as E sometimes. That equals stress over strain. That means there's a relationship between stress and strain. And there's this equation here, which we found rather useful last week. We can save ourselves a lot of time if we can figure out what it is we're trying to get, figure out what equation we're going to use. But this equation here we found very useful, because it meant rather than do half a page of calcs, you do one line of mathematics to get the correct answer. That's what we found. This here in blue, we refer to that as the axial stiffness. Stiff is the axle or the rod. Okay then, so axial strain, what is it exactly? We're going to try and have a look at that in more detail. If we look at our rod, or my pencil, and we divide it up into multiple sections to an infinite number, and we then have a look at just one of those. Now if we assume if I'm going to pull down a load on that, all of these will all have the same load applied. Each one of them should have, or should all act in the same manner. Okay. Now this is before rupture. This is before it starts to go into that plastic phase. It goes into its plastic phase. At some point somewhere there'll be a part that's slightly weaker, and it will go into the plastic phase first, and it will start to be like plasticine. But we're not talking anywhere near that. We're just talking like a metal rod or something that we're pulling down upon before it gets to the plastic stage. The plastic stage, what is that again? That is right in my eyes. Plastic stage is the load being applied goes way beyond the elastic phase. Remember that. You got taught this last year by Juan. Is that right? Yeah. Excellent. So, essentially dividing up that rod into a very large number of parts. Let's just say I can't even pronounce the word. Infinitesimally small part. There we are. And this is the notation just to say that for I equals 1 to n, and n can be an infinite number. That's all that that's doing. So dx is the height of 1. And then when we've got it elongated, it's just dx plus strain. All that is. That certain amount. Total length of the rod, Li, is then equivalent to I equals 1 to n, for however many times you've divided that up. That. Not hard. Okay. So therefore, delta equals Li take away L, so this is the delta part, and then it also equals the sum of strain I. I equals 1 to n. It's straightforward. That there. I'm going to try and pronounce that word again. I always mess it up. But as n approaches infinity, that's what that's trying to say. Obviously, it will never equal, dx will never equal 0, obviously, because it can't. It will get smaller and smaller as n gets bigger, of course. So maybe move this out your way. Can you see that screen okay, yeah? I can. So, calculus last year, yeah? These guys do calculus at college. 7 years ago. Don't worry. I forgot on it as well. There are some cheat sheets. That book I showed you last week, the little red one, the Engineer's Pocketbook, you can download that. You can get it from the library as well. And there's other books you can get. It'll give you. There's actually quite a number of books, to be honest. For engineering, if you use that one I've given you, that PDF of the book with the mathematics through application, it'll also have calculus cheat sheets in there as well. But there might be some better ones that are more useful, just because you don't need too much calculus. So essentially what we're saying now is that there, i.e. delta, now equals strain dx after you've formalised it. However, I can simplify that down again, write it as strain times L. So delta, once I go through all of these steps, after that step there, it can just be simplified as strain times L. So that's the part you want to remember.
Incoming voice call from Wojciech Plaza.
I'm in a class. I'll come to you after I've came to the class, after I finish the class. Okay, mate. Having the lectures. Are we okay? Can I move slide? Right. Sorry, yeah, I don't know why I've done that. But yeah, it's simply that there. That's the thing that you want to remember. Strain equals delta divided by L. See, whilst I'm on that, what can I do? Let's go here for a second. If I can do this. I showed you this last week. I need to do this a lot. Just load it up, okay? And what was the thing we're having a look at? It was strain delta L. And that's not, there we are. Strain delta L. What I tend to do, again, it's because of how my brain works. I used to struggle with this sort of thing. So as soon as I figured this out, it made my mathematics much easier. You can see the delta L, delta's above the L, so I've drawn it as that. Here's my pointer. Delta L there, and strain there. I know this is a very simple one, I don't need to do a triangle for this one, but I would do that. And then if I wanted to know what L equals, well, that's just delta strain. If I want to know what delta equals, just strain times L. Make sense? Proof like I'm treating like babies now, but it helped me. So I'll get shot of that, and then I will go back to actual what I should be showing you. I've got a funny feeling that you guys are a little bit better at maths than perhaps last year or the year before students. I noticed last week you you all had the answers. And there's another guy that's not here today that I was really quite impressed with as well, that just had it sorted. Where last year's class, it wouldn't be quite as good as that. So I'm quite impressed with you guys. It's excellent. Right, so let's move on. So Parsons effect, some French mathematician. We will get an image, not a photo, an image of him in a second. Let's take the infinitesimally small part. This time, no longer of a rod, but actually of a solid object. So it could be a part of a beam or a column or whatever it happens to be, and there's loads being applied to it. So we can see the dimensions. I'm going to apologise to people who were brought up in the UK. Depends how old you are. How old are you guys? How old are you?
35.
Yeah, I'm going to apologise to probably you then, right? Because I was the same as you. We had in mathematics X that way and Y that way.
I was looking at that and I was thinking that bugs me, yeah.
Yeah, that bugs me as well, right? Now, you're just out of school 2 years ago, yeah? See yourself. You've all been taught this in school this way then, won't you? So your school teachers are still old. Right. In Europe, you do things more like this. In the UK, we're weird. We drive on the wrong side of the road as well, and we buy our petrol. So I'm on a rant now. We buy our petrol in litres, but we're talking about miles per gallon. Right. Anyway, so that bugs me as well. But when it comes to Eurocode, though, Eurocode for design, that's steel, concrete, timber, we need to think more like this. Anyway, let's just move on. We're going to apply a load to that original. Go back to the original. Sorry. Right. There's the original there. There's no load applied to it. You're going to apply a load to that. We're going to apply the load in the vertical direction. We pull it like that. It's going to change shape, isn't it? It is going to change shape. Even though it's steel or concrete, it doesn't matter. It will, in theory, it will change shape. Remember, it's a tiny little small part we're looking at, but there's a load applied. And so that delta here, you need to know what's happening. So it's a force over an area, but the force isn't it's a tensile force. So we're going to have elongation here and shortening in both directions there. All makes sense, pretty simple, straightforward. It's nodding if you agree, and if they don't, right, okay, good. So let's have a look at the notations. Now, the notations are very important. They are very important because if you don't understand the direction of the forces, then you mess it up. Your equations will mess up, and you'll get the wrong answers, and you'll lose some marks. Yeah, because you've got it wrong. So you will have to keep close eye on the directions and what things are moving. So if we look at, I'll use my mouse. Have I got a pointy thing? I have a pointy thing. Right, good. So let's go vertical in the x direction. That's a stress, the symbol for stress. So it's force over the area. The force is a tensile force. But in this direction here, we've got y and z, and that is the strain. And then the strain in the x there. Right, okay, good. We've got that sussed out. There's this guy here. Pretty sure he's French. What's his name? This elongation extension is called the Parsons effect. Actually, it's called the Parsons ratio. It's a ratio we actually use it as. In fact, we'll see quite a lot of this sort of thing, not just in this example here, but throughout nature itself. It's a very influential mathematician and engineer. You call a mathematician because it's pure basics, fundamentals, what it is. So the Parsons ratio for a material property identified as, now it's not the letter V, but it's Parsons ratio. Okay, so draw it as a curvy V if you want. Parsons ratio is the strain, it's minus strain elongation. Sorry, start again. Parsons ratio is the minus strain lateral divided by the strain longitudinal. Right, this is where an awful lot of people can mess up. Last year, my students, I think they all got it sussed. I don't think anyone made the mistake, but I did stress to them how important it is. So the longitudinal direction is the direction of the normal stress. Let's sink in. Let's try and figure it out. The longitudinal direction is the direction of the normal stress. Well, the stress, obviously, well, where is the stress at the moment? Think about what your head is, where the stress is. In this case, for instance, strain longitudinal equals strain x. Obviously that's going that way, so that'll be going that way, isn't it? It's fairly straightforward. Right? And so therefore, strain x equals Parsons ratio minus strain y divided by strain x. If the normal stress were applied along the y direction meaning this way here, obviously things would flip around slightly, and it would then equate to that. Make sure you get your head around this, because if you don't, you then have these two switched the wrong way, and then everything messes up. You get answers that are wildly wrong. The nice thing about when you get answers that are wildly wrong, what any good engineer should do is look at the answer and go, does that make sense? Can that rod extend 5 metres if it's only 200 mil? No, it can't. Type of thing. So just make sure you look at the answers and go, have I made a mistake? Right, I've made a mistake. Where have I made a mistake? It could well be you've got these messed up. If you're still struggling with that, go back afterwards and look through the slides. Get it until the penny drops, then you should be fine.
Andrew, just because they've used like X as the vertical, and that just in that, are we gonna have to do that as well, or can we just the horizontal?
One more time, sorry.
So in there, they've got the drawing X as like
Vertical.
the vertical.
As you were taught at school.
Yeah, we weren't taught that. So X.
That's a shame.
Yeah, X is the.
You need to think like an engineer, and we're in Europe. I know we're not in the European Union, but we are as a part of Europe. And if you want to get a job anywhere else in the world, that's how they'll think. And my recommendation is, no, I'm going to get my soapbox again. I know that our political parties had a thing recently about moving back to imperial feet and inches. That's a part of the manifesto for the last election. The election's coming up. They actually done that. They had a public consultation and the public said stuff that we're not moving back. Yeah? But because it was a manifesto, they had to have that consultation. I think but we've got X and Y in our schools is a legacy problem. It's the same with buying petrol driving your cars miles per gallon and there are road signs in miles, but everything else is trick. Up to you. Try not to think of X and Y then. Think about where's the load, what way is the load being applied. And if the exam paper says that vertical is X, make sure you double check that. Regardless of, I'm not into politics, I really hate politics, but regardless of what system they've got, check what the exam paper's got. It should have something like that in there if they expect you. Or better still, if they're wise and they don't give you any direction at all and they don't name anything, you still have to think in the terms of longitudinal, lateral. As long as you can understand the difference between these two words, longitudinal and line with, lateral, perpendicular. As long as you can understand and have your head around that, then I think this whole system, put it in, this system here, sorry, is what I meant. You put that in the bin and just think about longitudinal and lateral. And remember, we're still talking about a 2D plane at the moment. This is actually a 3D object. So we've got longitudinal, but we've got lateral. In this scenario here, assuming that that equals that, just to make it easy for my head, then that should equal that as well. If it's much detail. But let's assume that it's a homogeneous material that's all the same all the way through. A piece of steel, and these two sizes are exactly the same, then these two should be the same. That obviously won't. That'll be different. Sense? Yeah. Sorry about the X and Y thing, and it's just when it comes to Eurocodes, we do it slightly differently. The comma, you came across the comma thing yet?
Yeah.
I'm not the only person that said that. Other people have said the same thing. I remember working in a place before, and my calcs had to go to engineers, but they also would have to go to people that are non-engineers, and that would bug them. I was doing all my stuff to Eurocode. Yeah. Okay, let's get back to something. Again, this thing in text, remember this up here. The basis of the lateral and longitudinal is the primary thing you want to remember. So if we're looking at, this is an elevation of what you saw before, being pulled apart. This is the vertical direction. So the strain, is that right? Because that's the stress. This is stress and strain over E. Perfect. Yeah, so that makes sense then, yeah? So the strain X equals the stress X over E, which aligns with the equation you've had before. If a normal stress in the Y direction is applied as well at the same time, so we're pulling it apart vertically, but we're also compressing it in the Y direction, what's going to happen to this 3D object now? Therefore, a further component of strain will also occur along the X direction. Okay? This is fairly normal for an object to have more than one load applied to it at one time. Slow down so people can write down. And remember, at the moment we are still talking about a very small part, like a very small part in a larger beam or a larger object at the moment. We're not. What time is it anyway? We should probably move on a wee bit quicker. No good? So then, for such a case, y is the longitudinal direction. Therefore, wait a minute, is y, how is y longitudinal direction here? Any thoughts? What have I even said here? Pulling it that way, but we're also compressing it this way here. Such a case, y is the longitudinal direction. Therefore, Parsons ratio, that would make sense. That's the lateral, that's the longitudinal. What am I saying here? Why would that be the longitudinal direction? Is it always going to be the longitudinal direction?
You've rotated the object. So now
One more time?
you've rotated the object.
No, I haven't. It's still the same object. Still this 3D, so
So we're still sitting at the same plane we were initially sitting at.
yeah, so this is the one who were pulling it this way.
Yep.
And it was getting smaller, right, like that, to this one here. And then after we've done that, we then applied an additional force. So what did we say before? We said before, if I go back several slides, right, I will go back to that slide. The longitudinal direction is the direction of the normal stress. So therefore, the longitudinal is that. So we're pulling it, that's the longitudinal there. But what all I've done is, I then switched it this way as well, haven't I? So, what? Jumped a bit like a lunatic here. There we are. I would say, in such a scenario, treat this as a statement. In such a case, y is the longitudinal direction. So you're not deciding it, we're telling you it. Hypothetically, hear me out, my load here could be absolutely massive. Let's call it 10 newtons or micronewtons or whatever, but a big force. And this could be a tiny force. I've not switched anything. But for this example here, we've told you that the longitudinal direction is now that. So in this example, we have switched it because of we're applying a load. I know, I'm just saying, for this, read the wording. We're telling you that it has, not asked you to identify if it has or it has not. We've told you that it has. We've now given you the direction. Because we've given you the direction, got that. However, whilst we're here, that doesn't mean that holds true in every case. Because it could be the big load, small load, and it's not going to switch anything. At some point it will switch. You don't know that until you do either further mathematics or somebody tells you. Make sense? But for this just now, we've told you that it has, so therefore the load's such that that is the case. I made that as clear as mud.
You've pretty much said if the question tells you that's the longitudinal direction, you just do it as that.
Exactly.
Okay.
Exactly, yeah. That's exactly it. However though, hypothetically, because I've not told you any forces yet,
Yeah.
let's just say one's tiny, one's massive. I might not have changed it at all. because I've now told you that I've given you the direction, for such a case y is the longitudinal direction, we now know how to manipulate that equation there to give us that. We've now got this. So that's nice and easy. So read the question, make sure that you're answering what you've been asked to answer. It might not be that you are asked to identify, because I think it would be too difficult for you to identify anything until I start giving you numbers, and this module we will not be doing that. You will not be tested on that, because that's a little bit further on as well. Right. Okay. So we can take what we've got here, normal stress applied in the x direction generates strain, blah blah blah, bang, and then all we've got here is the strain equals this from that one there, and this because of the stress in the y direction. That's all that is. That is just two components. That is the first one of that being pulled that way, and that is the effect of it being pushed that way. You're just adding the two together. Make sense? And in actual fact, that's quite a good thing for you to remember. When you've got a complex system where there's more than one action being happened, break down to simple steps. Work out the effect of phase 1, work out the effect of phase 2, and does it hold value by adding the two together equals the result? In this occasion it does. I would suggest in your going forward that sort of approach where you do effect 1 and effect 2 might also apply elsewhere within this module. I move forward. I'll wait until you've got that written down. Again, this is quite overly simplified, but we are looking at it in a 2D plane at the moment, or as a cube, not a cube. Cube essentially. Oh, not a cube. This direction started off as the same as on there. Then it holds value. Then it holds true. Until people stop writing. Okay, you do it longhand. Just get down the equations, that's what you really need. So therefore, the normal stress Y is a compressive negative stress here. Right, let me get this right. Well, if it's compressive, it's going to be negative. If it's tensile, it'll be positive. Positive, negative, so that holds value. What direction's the force going? Then we can simplify this equation down to give us that, and that's just you manipulating that into that. That's all that is. It's going to be very helpful for you to know how to do that yourself. That will not be the same every time, obviously. If no stress component acts in the third direction, in the Z here, the material is in a state of plane stress. But we've got one direction, two direction, and there was not an additional force coming that way, then essentially if you were to do a sectional through that material, the whole material is in plane stress, not three-dimensional stress. Make sense? Last week, it was only axial stress, i.e. one direction. This week it's plane, two directions. Okay then, what time is it? What have we got? We finish at an hour's time from now, don't we? Right, so we've got two exercises to do. Do the same thing as last week. If you want a 5-minute comfort break, you can do that now. If you want, we can come back and we can then have a look at this question here. We've got two of them. Then I'll set you up a tutorial for next week, which you can do midweek. You get it to me hopefully before Friday night or something. Get it to me on the line. On a 5-minute break, and just to carry on. We'll just carry on then, yeah. So exercise 1, a steel rod shown in figure is subjected to a tensile load of 400 newtons. The rod is 0.8 metres in length and has a circular cross section with a diameter D of 35 mil. Wait a minute, this sounds awfully like the exercise from last week, doesn't it? Steel has an E value of, wait a minute, normal steel. So 210,000 newtons per millimetre square. We found that the strain longitudinal for that are a ratio, millimetres divided by millimetres. Actually, whilst I'm on that note, it's actually very useful for you to don't say zero, don't say it's unitless, don't just say it's a ratio. It is a ratio. Technically it is unitless, technically, yeah, it is a ratio, but it's actually very helpful for you to write down what it's a ratio of, because when you want to manipulate your equations, if you don't know what that ratio is in, then it's not very helpful. It's helpful if you happen to also know what the ratio, how the ratio is made up. Right. So what I'm going to do ready that first of all, not anymore. This is your same question. You read that okay, first of all. And that's just my notes to the side, just so you can figure out what it is you'll want to use. What I could do is, in fact, would it make it easier for you? Probably would. Use that now. The first thing I would probably do here, write down all of the stuff you already know. We also know, I forgot about that, we also know the Parsons ratio. What are we after? Let's see how you're doing it. So you're not copying me, you're doing, I'm just getting you started. So, exactly, that's exactly it. So, no, it's good, it's good. So, the area of what? A rod, a circle. What's the area of a circle? Pi r squared, that's the diameter. That's the diameter. Put pi r squared in. You want to think about if the area is just pi r squared, isn't it? So write that down. But write it the way that reflects d. For fun, I'll just do it for you here. Pi. So it's not pi r, it's pi r after it's been modified. So it's pi I squared. That obviously equals d I, because we don't have r, we have d. I know it's just multiplied by 2. I know that. That's what you've got written down there. What do we not have here? Well, we know what this is. All of that. The only thing we've not got, we don't have that, do we? Let's try and figure out what that is. That's the diameter of the rod after it changes. So in my set of equations here, what have we got to use? Just start writing stuff down. Just try and work it out yourself. Look at your notes as well. That doesn't work. What I wanted. Make sense? And a lat just means lateral. Try and do it yourself. Try and do it before I do it.
They're messed up online.
Are they? No, they're not. Sure, they're not messed up online.
It's one like that as well.
PC.
Yeah, I've got like a.
Yeah, it is.
Yeah, I know, it's just normally for all the other ones.
Right, I feel what I've done is I've given you the PowerPoint.
Yeah.
You know that's a PowerPoint file, aren't you?
Yeah.
You need a PDF file.
Oh, okay, right.
Do that. I'll have that done for next week as well.
On my phone.
Yeah, to get the answers. Maybe, no.
No, it's just, yeah, because
No, that's fine. I'll do the PDF for next week as well. For going forward.
Yeah.
I never thought the mobile phone would mess it up. But the reason why I took down the PDFs, I plug my laptop in, is I change the slides every year. I either fix 5 errors or do things. So I took away the PDFs from last year because I didn't want my errors to reappear. If that makes sense. There's an error. Was an error in this module a year, 2 years ago now maybe. And the first time I saw it, I thought, right, I'll fix that. Never fixed it. The following year, it's there again. So hence why I'm going right now. I need to take down the old PDFs. I'll put fresh ones up every week. That's what we'll do. Yeah. Answer?
Yeah, I don't know, I was wondering if you could look at it and tell me if it's...
Yeah, of course. Give me a second, mate. Let's see if I know the answer first. Let's have a look. All you're trying to find is, yep. I don't know the numerical answer, I only know the equations. Only mathematics. Yeah. So, and how does that differ from the original idea? It's only what? Say that it's wrong.
Yeah, I don't.
Say that it's wrong. Well, believe it or not, it's actually really easy. It genuinely is. And I'm off at one more line to finish it and you have the answer. So when you look at what I've done, so I've got my area I, my finished area equals that diameter I, i.e. the changed diameter, we don't know. So I know that my stress strain lateral equals delta D. That's just the change, that's just delta, that's all that is, i.e. that equation there. So I work out, well, that then equals, it's just that rearranged to give me that. Now, what am I going to do now? Is it? We can finish early anyway, it's fine. Right, so let's just have a look at this then. What do I do now? I've got my lateral, so my strain lateral equals blah blah blah, and then I've now got my, I've made a simple, no, it's good. So I know the equation for Parsons ratio. So I'm going to use that. Oh, sorry. So I know that equation. I'm going to rearrange that to get what I need. So I need nice to me. See that? Yeah, you can. Good. That. Because remember what I'm missing at the moment. I'm missing that. So rearrange this. That's going to equal minus sign. Ratio. Better handwriting, it'd be dangerous. Enjoying this as well, but not anymore. Ratio. Strain longitudinal. I've just rearranged that to pull that out. And so it's going to be minus sign that times that. Gives me this. Now I'm cooking with gas. Now I've got everything that I need to get my answer. Make sense? Once you finish writing that down, we'll then actually have a look at what the answer is. Say that it's easy, but it's only easy once you see it. And perhaps my notes are too small. It's difficult to read my notes, isn't it? Right, I'm going to finish writing down it and I'll move to the... Here we are. I'm sitting down now. I'm sorry, guys. But again, we'll go through it very quickly. I'm trying to find calculate the reduced cross-sectional area, that's AI, for the effect of the applied force F. We've got AI equals pi r squared. That simplifies down to pi di divided by 2 squared. And we don't have di, so we're trying to find di now. We know the equation strain lateral is delta divided by d. So di take away d is delta, the change in the diameter. So it's the di that we're trying to find though. So we use that triangle approach that I was showing you before to figure out, well, wait a minute, that's just going to be, yeah, literally that. Okay? And then from that, what I don't have the lateral, strain lateral. I know Parsons ratio has lateral in it. There's the equation there. I pull it out. Or strain lateral equals minus Parsons ratio strain longitudinal. And now I have everything that I need. From before, I've got everything else. I can then just start populating it, getting my answers. And so, how far off were you then? A good bit. A wee bit, yeah. Did anybody else get anywhere near the mark there? You did. Let's have a quick peek.
Because I'm around and I ended up getting a wee bit of a different answer for
Perfect.
the final one.
Perfect. Right. Sorry, let's have a quick check again. Okay, that's actually something really good to talk about. Normally if you had done that midweek and someone sort of put it on the slide, I'd take your name off it obviously and I'd talk about it, but let me just talk about it now. What you've got is rounding errors, but your rounding errors are compounded. Actually compounded rounding errors. So you're actually out by quite a lot. Even though what you've done is perfect, you're out by more than 0.5 of a millimetre square. Sounds like nothing, doesn't it? But that's actually quite a compounded error that you've got because of the amount of decimal places you've used further up. It's not very high in decimal places. So, would you have lost any marks for that? Actually, you probably might not. You might actually. You might lose some marks for that sort of error, maybe. So what you want to do is you want to think about how many decimal places do I want to use for each of them? How much is acceptable? I mean, if you lost anything, it'd be like half a mark or something. It wouldn't be much. You want to think about what your errors are going to be and how far should you go. And how far is way too much? I think what I've got here is absolutely fine. Let's have a look. So we've got 1, 2, 3, 4, 5 decimal places here given to you. And on my example, I also converted, let me just go back to this for a second, guys. Here, I took my data that I was given in green, put a line down, and I converted everything from green to red. And from then on there, I used everything that's in the red. I forgot about all of that. The reason being is if I don't do that now, me trying to convert unit to unit after I've got the answer will be very near impossible in an exam situation. So it's better to get your units, looking at years 2 in particular, you were only here last week. Always convert your data you're given into something consistent, first of all, when you first start. If you do that, you won't make any mistakes. So,
See, when it comes to the exam,
yeah.
how many decimal places should we be using?
That's what we're talking about now. I don't think
I'm just wondering.
there's no right or wrong answer.
Because that's what I was wondering when you're saying sort of like a reasonable number. I was thinking, is it looking for 5, 6, 3? Or...
I'm going to use a get out of jail free for me. It's your engineering judgment. So if you think, if you know the equation, so at this point here, there's no maths involved, there's no arithmetic involved so far at this point here, but I've got all the maths done. I now know at this point here, I now know I have got everything. I've got my Parsons ratio at 0.3, I've got my strain longitudinal, that's that number there. I've got everything else. I can now answer that question. At this point, I should look at, well, how many units should I have a look at? On your beautiful example, it's very well neat handwriting as well, by the way. Much that I love seeing neat handwriting. I'm terrible. Mine's is.
That's why I didn't call you over here.
Just think that once you've got to that point there, I firmly recommend what you do personally is you don't do any maths any arithmetic until you've got the maths sorted out first, and then do the arithmetic. At that point there, figure out. So we've got 1, 2, 3, 5 there. Stick to 5. That's what I would do. That's that simple. It is engineering judgment, and you'll be using that phrase for the rest of your life. There's another phrase for it. my brains went blank. As a structural engineer, we look at a project and we look at a part within the project, reasonable inspection, no. Sure. I used to write it all the time. There's something that was so stupid that you would go, that passes inspection, you would say, I'm not going to calculate it because it's irrelevant me calculating that, it's just passed reasonable inspection. That's not the phrase. I'll remember the phrase for you for next week. In my calculations, you say, engineers use this phrase all the time. Right. Building control call it reasonable inquiry, but that's off the script here. So for here, I would probably just pick 5 and go with 5.
General rule, if we kind of use the number of decimal places of the largest or smallest.
Absolutely not. That's not the rule. What we're trying to do, because that would not hold true for other scenarios. What you're trying to do here is you're trying to look at a very small part, a very, very, very small part. And when I say that you're out by quite a lot, it wasn't really. It was out by 0.6 or 0.5 of a millimetre square. That is nothing. It's absolutely nothing. But remember, what he's looking at is something that's not very big. We're trying to be here. We're trying to be precise. But when we're building a building, like anything you see out here, I told you this before about the engineer that taught me years and years ago. He used to look out in windows like this and go, I can see 14 buildings that I've built. Yeah, and it was a slide rule we used to use to calculate. He was old, right? In Edinburgh, very few of my buildings are still in Edinburgh. I've got a lot of buildings elsewhere though. When it comes to big buildings, a millimetre is not an issue. For this scenario here, we're looking at material science, then yeah. So that's not always, as engineering, you have to judge for yourself.
It's just when it comes to the exam, just don't want anyone to lose out on marks because
if you have your handwriting neat, or just and do the mathematics first, and make it nice and easy to read. You'll know those marks because of that. And then if you do all of that nice, it's easy for me to follow, or whoever marks it to follow. Then you do the numbers. If you do that nicely, you'll probably not lose any marks. When people do stuff scrawny, really horribly written, in fact don't even do all of this, it's in their head half the time. I see this quite often. They'll put down blah 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 and they'll not put out the full equation. They know how to do it, they know it, but they don't write it down. And then they put numbers in, like where did that number come from, and numbers wildly wrong as well. Then you might lose some marks. Always take your time in the exam. You always get more time than you actually need, than what you should need, to be honest. Just take your time, don't be rushed, and write out things nicely. You need to be longhand like what you're doing. You're writing paragraphs of text out. You don't need to do that, but you do need to write the mathematics out. Make it legible, you'll be fine. Yeah, sorry, where was I meant to be going here? So after this though, what I can do is I can then talk about the reduction. So that's actually a reduction of 0.12%. What that is. Okay? That's one thing you didn't do. I never asked you that though, but I'm giving an example here. And you then say that's a reduction of bang bang bang. Okay, second exercise. Now, this is actually, it's a hypothetical exercise. I should really change this one for next year. Just go with me on this one, okay? Just go with me on it. We have wall subject to a line load. Imagine it's a homogeneous material and it's in my perfect little world, okay? And no other influencing factors on the wall. So a line load of Q, which is 1,000 kilonewtons per linear metre. The wall is 50 metres long, 2.1 metres high, and has a thickness of 100 mil. This is getting changed for next year. Right. Modulus of elasticity of 26,000 Newton millimeters square per millimeter square, whilst the Parsons ratio is 0.15. Compute the elongation of the wall, delta x. Elongation this way. Again, I'm going to acknowledge I probably should change this exercise because we as engineers generally think of the real world, a real world scenario, and it's 3D, and it would also bow out this way. It's only 100mm thick, the wall would bow this way as well. Forget all of that, none of that's happening. That's just my imaginary world. What would happen with only the forces that I've told you about. About your time on this one. Again, if you've not got your written notes from today, I'll have that here. Is that legible, yeah?
You need to make it a bit bigger.
Yeah, I was thinking that. Is that okay? You've not really seen my notes though, are you? You've not really seen my notes over here though, is the only problem. Is that okay? I can do it without the notes actually. I could just do this and make it much bigger. How's that? I'll just do that then.
Slight tangent. Why in this term is x that way and y that way? Is it because we're just saying it's stretching that way?
Because it's an exercise that I stole from someone else.
Oh, right.
And yeah, hence why I was apologising. I'm apologising for this exercise on so many accounts. One, the exercise is, it's not real. Wall, 100mm thick wall, 2.1 metres high. The wall is going to buckle this way, and it's going to elongate not just this way, it's only going to get fatter as well. It's going to never work.
Maybe the wall's constrained by something very...
Imagine it's a hypothetical world and it's in a plane. Now, so today we're looking at planal stress. Plane stress. So assume that it's not allowed. Oh, sorry, mate. Assume that it's not allowed to buckle that way, okay? It's allowed to bow that way. It's only 100mm thick but 2.1 metres high. Imagine it's not going to fall to bits on me. I'm going to have to change this for next year. I don't like this one now. And that no longer follows a convention. This has been stolen from somewhere, obviously. Should just redo some of these exercises I've won. I'll do that. Well, I'll create some additional material for prep work for your exam. I'll create some nice new ones for you to play with. And I'll then steal some of them from my lecture notes and get rid of that one.
Are the exams in class?
It'll be a class test.
So like,
Yeah, in here. not this room, but a room like
Yeah,
this.
that's fine.
It won't be at Sight Hill. That's what they're trying to do. They're trying to make timetabled exams at Sight Hill, and I'm going. I don't want that. I want it as a class test. Otherwise, you have to go to Sight Hill. I have to go to Sight Hill. It's unnecessary. Also, I want full control over what I give you. If I wasn't closed book, I want it closed book. I bored people last week why I think closed book exams are good. In real life, set at a table for an engineer. Oh, that's they say, oh, what about people the cross using fancy answer you got. Amazing. It's good. A wee bit. That's fine. Maybe that give you a pumpkin of thousands on it. In the next 2 weeks, you'll look exactly.
Week 5.
No.
No?
The exam will be like week 13 or something. This time I'll have figured out what.
I was looking at the thing on coursework or something.
Well, you've got coursework. You've got lots of coursework. Lots of coursework to do. But you've got 3. They're really simple, easy. Your first one will take you 2 nights. This 2 will take you 1 night each. That's what I reckon on average.
Oh, that's fair.
What the class is, then. That's fine.
Your courseworks will be really easy. The first one will take you longer. It'll be the first one you've done this way. Once you've done that, you use the same method to do the other 2. The other 2 will take you 1 night each. That's it, no more.
That's all right.
I'm doing handwritten stuff up here. Would that be helpful? I know you've got it all on the lecture slides, but would it be helpful to have the handwritten notes as well? Put it in the middle for you, right? I can work out how to do that. Hopefully you've already done this, you've already written it out, hopefully, if you haven't, try and do it before I do it. Write down all the information you already know. Get the habit of doing this as you go. It'll help you fathom out how you should be doing it. I don't know, I'm just going to guess here. I'm going to use kilonewtons and meters, because actually this is why this is in here. I'm an idiot. I probably should keep this exercise. Even though I don't like this exercise, because it makes no logical sense, and my arrows are not following the European Convention. What is good about it is that what I'm about to do now, I'm going to convert the information I've given you into a consistent set of units. Because it is quite a large thing, I'm going to use meters, and the loads are massive. I'm going to use kilonewtons, so I'm going to literally just do that. Meters remains 50 meters, 2.1 remains 2.1, and 100 millimeters just. So I think this is why I left this in here the last time, is that converting it to something sensible, or for what it is we're looking at, does make more sense. And what's it we're after again? We're after the elongation, isn't it? You can't see my notes. As long as you've got your notes, it's a bit easier for you. I don't have that. I don't know why I done that. That was stupid. An idiot. So what I was trying to say is, I don't currently have that. I do have this though. I'm going to write down, I'm going to try and get that now. I know from this equation here,
That's not on screen.
oh, annoying. Annoying. 2 monitors. I know that I've got this here. I'm going to use that to my advantage. Just write that down there the now. Ratio, the black pen, Parsons ratio, and it's minus strain at LAT. Oops. I did it too small with my problem. Go a bit bigger. double check I've got that right. Cool. Now remember what I'm trying to get. I'm trying to get my then, what am I doing now? What am I doing now? Remember, where's my direction of travel? No, travel, sorry. Where's my direction of strain? Here.
Why direction?
Thank you. Well, before I do that, let's do this first of all, yeah? Ratio. Okay, cool. Will we be given? Well, we do have Parsons ratio as well. Got to write that down. Okay, cool, right. Bit messy. I do apologise for my messy handwriting. That makes sense? That is messy handwriting. That does not look good at all, does it? So Q is my load my linear load, times L, which is the length, divided by the breadth times L. So that's the stress in the y direction. So the stress coming down is the force over area times the length. Or no, it's not force over area. It's force length. And that's it. It's the Q, the linear load, times the L, gives you the actual force. The bread, and that's the area. So that there equates to FA. Essentially that equates to, and you remember that equation from last week? Make sense? I'll show you what I mean. Oh, don't do that, don't do that. That would be too clever. Here we are, this equation here. Right, that's what you're mimicking just now. Force is the linear load multiplied by the length of the load, gives you the actual F, and the breadth times the length gives you the area. So you've now got that. My handwriting is amazingly bad. And remember, we're still trying to find this. Okay. How are we doing for time, guys? Are we? We've got 9 minutes left. So has anyone sussed it out yet? I'm doing it very slowly here to allow you time to actually try and figure it out. Well, from this now, we have Q, L, B. Have everything. Actually got it all now. I've got blank faces. What we'll do is we'll go back to this then. So if we write down what it is we're trying to find delta x that we've got so far. And now that we've got strain, stress in the y direction, the vertical direction, is Q times L, which is the force, divided by the area, which is B, the breadth, times the length. You can calculate that as negative because it's a compressive force. Bring that back up, and that, calculates it all out. So the overall wall would extend by 5.7 millimeters.
You change Q to newtons then instead of kilonewtons.
On this occasion here, on my slides, done this a couple of years back now, I converted everything to a different unit. I converted it to millimeters and newtons. So I could do that. And now actually, if you want, that's make it more consistent. So that would be No, let's have a look at that. Was anyone got the answer for me in this one? I want to convert this to, move my mouse out of the way. I want to convert this here, kilonewton meters, per linear meter. I want to convert it to, use your phone if you want. Units per millimeter.
2,000 times 10.
Sorry, hold on. Somebody just said the answer. Sorry, what was the answer?
So 2,000 times 10 to the 6, so 2 times 10 to the 9.
Converting it from kilonewton per meter to newtons per millimeter. What, someone? And length, that would just be what's the answer, anyone? I'm going to come to you. I'm going to trust you on this. Am I wrong?
Yeah.
Makes sense.
Times 10 to the 6, and you have 3 extra zeros.
Okay, so what I'm going to say is, it doesn't matter if you convert it to newtons and millimeters, or kilonewtons and meters, you will still get the correct answer, as long as all of your things are consistent. So long as you keep that consistent, I'm doing that. Right. As long as you're consistent, then you're good. It's when you're not consistent, you've got some units in meters and some in millimeters, then your maths just go to pot and things don't work out. What I'm saying is, make sure you convert stuff at the very start and have it all consistent, and you'll be good. So that the end result is the elongation of L is 5.7 millimeters. Cool. Weird example, but there is stuff of value in that example. You can see here though that these are quite good at body language. I'm not too sure. You're following this, aren't you? You definitely are following it. you're not writing much down. And my body language, like, I thought we kind of all got stuck when we got to here. Is that correct? Everyone, when we got to about there, were people still stuck? You shouldn't have been, because at this point here, you now have, well, sorry, until the numbers went in. So when you're there, and you know you've got that, you've got all, you've got all of those 4 terms. You've got all those. That means you now have that. You now have that. You've got that. You've already got that, which means you've now got that. Already have that. That is 0.15, which means you've now got this. You've got that, you've already got L, of course. You now have the answer. So when you got to this point here, you should have said to yourself, bingo, I've now won, I've got it. And then you just do the mathematics. That's all that's happening here. Make sense?
Yeah.
So it's backwards. We're doing problem solving the backwards way. Well, we're just trying to figure out what all the mathematics is first, then we do the arithmetics. A lot of people would go arithmetic first, or as they go. I would suggest try it this way instead. So we've got a tutorial for you to play with midweek. Let's see if I can find it for you. And I will put up the PDFs for you as well, so you can use your mobile phone and not just rely on a PC. I will have to change. I'll put up a new version of today's lecture. Here we are. This is your tutorial question for this week. Just read through it. A solid copper circular rod with a diameter of 40 millimeters and a length of 800 mil. The Parsons ratio can be found in table 1. It's not called table 1, but let's assume that it's a table. Copper, so down the table, let's find copper. So there's my Parsons ratio, 0.33. Okay, that just came off the internet, by the way. Now, Young's modulus can be found from, and I just stole it from, there's the link there. There's the Young's modulus there, okay? You'll have to convert GPA. Anyone know what that even stands for? Sorry?
Gigapascal.
Pascal was perfect, yeah. Another French person. Excellent. So, calculate the force required to reduce the cross-sectional area by 5 millimeters. That's meant to be square, 5 millimeters square. You try to calculate what the force would be to pull that up, be required to reduce that area. Now, again, please just assume that in my perfect world that no other forces are acting on it and it all behaves like a homogeneous material, meaning all the same throughout. Once you have your answers done, don't email it to me, ignore that, that was for last year. Don't email it to me. Put it into here, please. Right, can I do student view? Control. Yeah, that's more like it. Yeah. Your tutorial, additional for week 3, and submit it into there. Try and do it before Monday's class. Try and do it for Friday night, actually, if you can. That'll give me some time. What I want to do is, I'll anonymise it. I'll make sure your names are not present. I'll make maybe some lecture slides or some sort of slide out of what you've done, how you've done it, and so do give it a bash. Even if you know it's wrong, please admit it, because there may be something valuable in we all learn from where you might have went wrong. Does that make sense? I will anonymise it, and I'll not then point out, blah, 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 somebody made a mistake. I will not do that. I'll try and make sure it's a learning material. All good? Try and encourage your colleagues. I'm going to stop recording now.